As we have seen in class, the wavelength and frequency are inversely proportional to each other. Additionally, the wave speed is proportional to the wavelength. Thus, we can express this relationship as v equals lambda times f, where v is the wave speed, lambda is the wavelength, and f is the frequency. Remember, the frequency is the reciprocal of the period of the oscillation t, which we can express with f equals 1 over t. A concrete way to think about this equation is in terms of a wave train or a choo-choo train. Suppose the choo-choo train is traveling with a speed v. We know the definition of speed is change in distance over change in time. We can define each train car as one wavelength. So distance is equal to lambda. In a given time, delta t, the train travels an entire wavelength or one period of time t. Thus, we can substitute into the equation for speed and arrive that velocity is equal to the wavelength divided by the period, or wavelength times frequency. A nice example would be looking at Boston University Radio WBUR, whose frequency is 90.9 megahertz. Radio waves travel at the speed of light, so velocity is 3 times 10 to the 8th meters per second. So if we express our givens as the velocity is 3 times 10 to the 8th meters per second, the frequency is 90.9 megahertz, or 90.9 times 10 to the 6th hertz. The equation we use is the wave equation, or velocity is wavelength times frequency. We do some algebra. The wavelength is now velocity divided by frequency, or 3 times 10 to the 8th meters per second, divided by 90.9 times 10 to the 6th hertz, gives us a wavelength for WBUR of 3.3 meters. In class, you observed what happens to pulses and waves when they reflect off of a surface. You may have noticed that the FET waves on a string simulation allow you to choose a fixed end, a loose end, or no end. With the fixed end, the reflected pulses are on the opposite side of the wave. You could think of this as akin to bouncing a ball. You could go into greater depth and explore the boundary conditions. What this means is that the position of the reflected pulse just before it hits must be the same as the position just afterwards. Likewise, the speed of the pulse must also be matched. However, something strange happens with the free end. You might notice that it reflects on the same side. You can do this by hanging a slinky or a spring from the ceiling. You may also notice that something strange happens when a wave hits a boundary between two types of spring, such as a heavy spring and a light spring. In this video, you can see there is both a reflected and a transmitted pulse. What's interesting is that whether the pulses are reflected on the same side or the same side, different side, and the speed. For instance, in the video, you may have noticed that the speed of the pulse changes at the boundary. If you go back and play with the FET simulation, you will notice that the wave speed can be adjusted by changing the tension in the spring. The wave speed also depends on the inertia of the spring. You can read about how the inertia and tension affect the wave speed at hyperphysics. Essentially, we will return to this idea when we talk about tuning a stringed instrument. Other factors that affect wave speed for different types of wave. For water waves in the ripple tank, the wave speed actually depends on the depth of the water. The shallower the water, the slower the speed of the water. When doing waves problems, there's a few numbers that are important to have on hand for typical physics problems. Radio waves, X-rays, microwaves, and light are all forms of electromagnetic radiation, and thus travel at 3 times 10 to the 8th meters per second. Sound waves in air travel at about 340 meters per second, but this number can vary with air pressure, humidity, and temperature. Sound waves tend to travel much faster in a medium such as water, around 1500 meters per second, or even higher in a solid such as steel, over 5000 meters per second. What happens to the energy of a wave as it travels? As the wave travels, it loses a lot of energy due to the friction of the oscillating medium through which it is traveling. In turn, this means that the amplitude decreases as the wave propagates. You may have noticed that you can adjust the dampening of the wave in the computer simulations. Additionally, at the boundaries, the question arises, how much energy gets transmitted versus how much is reflected?